If you've been watching MasterTech for some time, you probably remember hearing about the new onboard diagnostic system. We first introduced you to Onboard Diagnostics II, or OBD II for short, in the January 1994 MasterTech. You might recall that the Neon was the first Chrysler vehicle to have this new onboard diagnostic system. By now, many of you have probably had some experience working on vehicles that use the OBD II system. But did you know that by model year 1996, almost all Chrysler vehicles will be equipped with OBD II? That's why in this month's MasterTech, we're going to equip you with the knowledge of OBD II you'll need to successfully diagnose vehicle problems. In this program, we'll go through a general overview of OBD II, including why it was implemented and which vehicles have it. Then we'll get into OBD II operation, looking at what actually happens during vehicle drive cycles. We'll cover OBD II monitors, including continuous and once-per-trip monitors, and the operation and importance of OBD II good trip counters and the warm-up cycle counter. Then we'll go through some examples of the onboard diagnostic systems at work. We'll also discuss what impact OBD II will have on you, the service technician. And finally, we'll introduce you to OBD II freeze-frame data and the similar conditions window, which you'll find are great diagnostic aids that resulted from OBD II legislation. As you probably know, OBD II is the result of legislation enacted to keep vehicle emission levels low. The two main pieces of legislation are the EPA's Federal Clean Air Act and requirements from the California Air Resources Board, or CARB. This legislation charged automakers with not only reducing vehicle emissions, but with monitoring the emission-related components and systems as well. While fulfilling these requirements proved to be a challenge for automakers, they increased the available data that technicians can use to diagnose vehicle problems. Let's take a quick look at the requirements of OBD II to see how they led to changes in vehicle emission systems. There are common requirements as well as some differences between the two pieces of legislation. We'll start with requirements that are common to both. Both EPA's federal and CARB requirements mandate that the driver must be informed when an emission-related system or component malfunctions or deteriorates, causing emissions to exceed certain thresholds. The driver must be informed no later than the end of the second consecutive trip in which a failure is detected. Chrysler vehicles maintain this standard by illuminating the check engine or service engine soon lamp. You may know either of these as the malfunction indicator lamp, or MIL. The driver must also be informed immediately if catalyst damage is about to occur due to engine misfire. This is accomplished by flashing the MIL, letting the driver know to ease off the throttle and bring the vehicle in for service. CARB OBD II and EPA Federal OBD also set requirements for diagnostic trouble codes, or DTCs. One requirement is that a DTC is stored in the PCM's memory whenever a fault is set. The DTC must also be retrievable with a diagnostic scan tool. This legislation also brought about changes in the codes themselves. The new DTC requirements are outlined in SAE Document J 2012. First, as you've probably noticed, the OBD II codes are 5 digits long, including a letter such as P followed by 4 numbers. Another change to the DTCs is that they must allow generic scan tool access, meaning independent service shops can read codes without specific scan tools. This also caused changes in the PCM. Additionally, OBD II caused changes to the data link connector, or DLC. Specifications for this 16-way connector are found in SAE Document J 1962. The change that is the most apparent to technicians is the location of the DLC. All OBD II vehicles must have the DLC located under the instrument panel near the steering column. Now let's take a look at some differences between EPA's federal OBD and CARB's OBD II requirements. The EPA has developed the following selected requirements for OBD to satisfy the provisions of the 1990 Federal Clean Air Act. One requirement is that the PCM must monitor the efficiency of the catalyst, the switch rates and heaters on upstream O2 sensors, and the engine for misfire. Other items are included under the catch-all phrase, any other component which can cause an increase in emissions. The EPA Federal Clean Air Act provisions also state that a failure is based on a certain increase in emissions. The CARB OBD II requirements may be used for 1994 through 1998 vehicles. The CARB OBD II legislation has the following selected requirements. The PCM must monitor the following: the efficiency of the catalyst or heated catalyst if equipped, the engine for misfire, the evap system or leak detection pump, the secondary air system, the fuel system for rich lean conditions, all upstream O2 sensors, switch rates and heaters, the EGR system, and all comprehensive components which can be defined as engine, transmission, and transaxle inputs and outputs. The CARB OBD II requirements also state that a failure is 1.5 times the federal test procedure emission standard, and that the federal OBD II requirements may be used on 1994 through 1998 non-low emission vehicles. Both federal and CARB have changes to the warranty requirements for emission-related components. For specific warranty periods, see the OBD II warranty requirements chart in this month's reference book. You've probably been seeing more and more vehicles with OBD II in your dealership. As we told you earlier, by 1996, virtually all Chrysler vehicles will have OBD II. Let's look at the vehicle lines that have it according to the model year. The 1994.5 Neon was the first Chrysler vehicle with CARB's OBD II. This includes all 1994.5 Neons. For model year 1995, several vehicle lines are equipped with OBD II. In addition to the Neon, they include the Talon 2-liter naturally aspirated with manual transmission, the Sebring Avenger 2-liter naturally aspirated manual, Cirrus Stratus 2-liter manuals, and all 1995.5 new minivans. By model year 1996, all Chrysler vehicles will have the OBD II diagnostic system, with two exceptions. Vehicles with diesel engines do not have OBD II until 1997, while compressed natural gas vehicles have OBD II without the major monitors. The 1996.5 4-liter Grand Cherokee will be the first Chrysler vehicle to be fully federal OBD compliant. Speaking of OBD II monitors, that's the subject of our next segment. But first, try answering this review question. How do Chrysler vehicles meet the EPA federal OBD and CARB OBD II requirement of notifying the driver immediately if catalyst damage is imminent due to engine misfire? A, the mill is illuminated. B, the mill flashes. Or C, the mill stays on after the engine is turned off. The correct answer is B. If catalyst damage is about to occur due to engine misfire, the mill will flash. In our last segment, you heard about the different items that the PCM is required to monitor. You might be asking yourself, how do these monitors operate? We could spend hours discussing the operation of the PCM's software that makes up OBD II. But let's take a general behind-the-scenes look at what the PCM is doing and why. For starters, there are two general types of OBD II monitors: continuous monitors and once-per-trip monitors. Let's take them one at a time. Continuous monitors, as the name implies, run continuously during vehicle operation, as long as certain conditions are present. These are known as enabling conditions. For pre-1996 Neon, Talon, Sebring Avenger, and all new minivans, you can view each monitor's enabling conditions with the DRB3 by selecting the Help function under OBD II Monitors. The PCM's Test Sequence Director, called Task Manager, requests a monitor to run only after the enabling conditions are met. There are two different continuous monitors, the misfire monitor and the fuel system rich lean monitor. These two monitors have the highest priority. The misfire monitor uses information from the crankshaft position sensor to determine engine RPM and indirectly infer misfire through cylinder-to-cylinder deceleration. The misfire monitor will turn on the mill in two different cases. First, if the misfire monitor detects engine misfire in roughly 2% of engine RPMs in a 1,000 revolution period, a temporary fault is set. These temporary faults are known as maturing faults. The PCM also records freeze frame data and the similar conditions window when the maturing fault is set. It takes two monitor failures in a row for the misfire monitor to turn on the mill for emissions increase misfire. If the vehicle fails the misfire monitor on the next running of the monitor, the fault matures, the mill is turned on, and a DTC is stored. In the other case, if the misfire monitor detects engine misfire in more than 15% of cylinder firings during any 200 revolutions, the mill will begin flashing, and a DTC is set immediately along with freeze frame data and the similar conditions window. A flashing mill indicates catalyst damage is about to occur. The task manager also watches for other conditions that may place a monitor on hold, which are called pending conditions. Pending conditions hold up a test until a related problem indicated by the mill is resolved. This can be seen on the DRB3 as the Done, Stopped Testing This Trip message. The task manager may also suspend the results of a test, like the failure of a monitor, for example, until another monitor, such as the O2 sensor monitor, has run and passed. Presently, there are no suspend conditions for the misfire monitor. Now let's talk about the other OBD II continuous monitor, the fuel system rich lean monitor. The fuel system monitor looks at short and long-term adaptive memory values to determine if the fuel system is in proper control. Once the enabling conditions are met, the fuel system is continuously monitored each trip. Since the fuel system monitor is a two-trip monitor, a maturing code, the similar conditions window, and the freeze frame data are stored on the first failure. The mill is not on at this time. But if the vehicle fails the fuel system monitor on the next trip, a DTC is set and the mill is illuminated. Like the misfire monitor, the fuel system monitor has pending conditions. These conditions are listed in chart form in this month's reference book. Those are the OBD II continuous monitors. Let's move on to the other monitors found on Chrysler vehicles. The other type of OBD II monitors are known as once-per-trip monitors. They check components and systems that control emission levels for proper operation. Once-per-trip monitors run one time during a trip and record the results as either done with no fault or fail, in which case freeze frame data is stored. Vehicles must meet the enabling conditions before a once-per-trip monitor will run. If the vehicle fails any of the once-per-trip monitors on two successive trips, a DTC is recorded and the mill is turned on. Let's run down the list of OBD II once-per-trip monitors and talk briefly about each one. The EGR monitor checks the operation of the vehicle's exhaust gas recirculation system. The EGR system is used to reduce the amount of oxides of nitrogen in exhaust gases and for increasing fuel economy. Once the enabling conditions are met, the EGR monitor turns the EGR solenoid off, creating a high oxygen or lean condition. It then monitors the short-term adaptive memory for the increase in fuel. If the change in the short-term adaptive memory's shift is outside specific values, the monitor fails and a maturing code is stored along with the freeze frame data. Since the EGR monitor is a two-trip monitor, a DTC is set and the mill is turned on if the vehicle fails the test on the next running of the monitor. The upstream O2 sensor monitor checks the O2 sensor's ability to switch from rich to lean, known as half cycles. It also monitors how fast the value changes, known as big slopes. This monitor can identify a marginal or sluggish sensor. If the O2 sensor monitor fails the first trip, freeze frame data is stored along with the maturing code. The mill will be illuminated and a DTC stored after 2 failures on 2 monitor runs in a row. The catalyst monitor checks the efficiency of the catalytic converter by comparing upstream and downstream O2 sensor switch rates. As the converter loses its ability to store oxygen, the downstream O2 sensor's switch rate will increase, approaching that of the upstream O2 sensors. If the downstream O2 sensor's switch rate exceeds the allowable limit, the vehicle fails the catalyst monitor for that trip. The PCM will record a maturing code and freeze frame data. And as with other 2-trip monitors, if the vehicle fails the catalyst monitor on the next trip, the mill is turned on and a DTC is recorded in the PCM's memory. There are other OBD II once-per-trip monitors that you should be aware of. One is the leak detection pump found on stricter EVAP vehicles only. The operation of this monitor is explained in the October 1995 Master Tech on New Model Highlights. The PCM also monitors the O2 sensor heaters, secondary air if equipped, and EVAP purge flow. Like the continuous monitors, all of these once-per-trip monitors have their own enabling and pending conditions. In addition, the number of monitors that are used varies from vehicle to vehicle. For more detailed information on these monitors and other OBD II operation, check out the Chrysler Technical Training course titled Onboard Diagnostics 2, number 083-0516. Now try answering this review question. What takes place when a vehicle fails a 2-trip fault monitor for the first time? A maturing code is recorded. B, the monitor's enabling conditions are recorded. Or C, the malfunction indicator light is turned on. The correct answer is A. When a vehicle has a 1-trip failure of a 2-trip fault, a maturing code is recorded in the PCM's memory. You've just seen some of the different ways the PCM turns the mill on. Now let's find out how it turns the mill off. The PCM has software contained in its memory called good trip counters. The sole purpose of these good trip counters is to turn the mill off after a repair has been made. The logic behind good trip counters is that if a fault that has been previously set does not appear in 3 trips in a row, the task manager requests the mill to be turned off. This is the OBD II way of letting the driver know that the original problem is gone and the vehicle's emission levels are within acceptable limits. Just like the OBD II monitors, there are different types of good trip counters. The first is the global good trip counter. The global good trip counter is used to clear faults that are non-misfire and non-fuel system related. The Chrysler version of a global good trip is to rerun the once-per-trip monitor that originally set the fault. If the vehicle passes the monitor, the global good trip counter records 1 good trip. Remember, the global good trip counter must see 3 good trips in a row with no failures in order to turn off the mill. The requirements for a comprehensive component good trip are the O2 sensor and the catalyst monitors running and passing. They do vary by model year and PCM type though, so refer to the reference book for details on comprehensive component good trips. Next is the fuel system good trip counter. This counter is used to clear faults that were set by the fuel system monitor. It must count to 3 to turn off the mill. The fuel system good trip counter checks the fuel system adaptive memory for rich and lean conditions, but only when the vehicle is under the same operating conditions as when the fault was originally recorded. These conditions can be seen in the similar conditions window, which is viewed using the DRB3. You'll hear more on the similar conditions window later in the program. The misfire good trip counter only runs when the vehicle is operating in the similar conditions window. It turns off the mill or clears freeze frame data that was set by the misfire monitor. The misfire good trip counter records one good trip each time it sees 1,000 revolutions of the engine without a misfire in the similar conditions window. It takes 3 good trips to turn off the mill. The alternate good trip counter is used only when comprehensive component monitors are stopped or pending. The alternate good trip counter records one good trip when it sees 2 minutes of engine runtime without a fault per trip. The alternate good trip counter increments the global good trip counter. The process for removing a fault from the PCM's memory is also different under OBD II. Prior to OBD II, 51 vehicle starts would erase faults. Now, OBD II uses something called a warm-up cycle counter. The warm-up cycle counter is used to self-erase a fault from the PCM's memory only after the mill has gone out. The warm-up cycle counter increases by 1 when the engine coolant temperature crosses 160 degrees Fahrenheit and increases 40 degrees in the same trip. For example, if ECT was 150 degrees at the start of a trip and it reached 190 degrees, the warm-up cycle counter would add 1 because it saw a 40-degree increase and ECT crossed the 160-degree mark. When the warm-up cycle counter reaches 40, the DTC that was stored will be erased, along with the freeze frame data and the similar conditions window if applicable. The readiness indicator tells you the status of all once-per-trip monitors. It may be used at emission test sites to ensure a vehicle has passed all OBD II monitors. Now you know what it takes to turn the mill on and off on OBD II vehicles. You've also heard about DTC storage and erasure. Before we move on, try this review question. How do good trip counters record a good trip on Chrysler OBD II vehicles? A, by having 2 minutes of engine running time. B, by running and passing the misfire or fuel system monitor in the similar conditions window. C, by rerunning and passing the monitor that originally set the fault. Or D, all of the above. The correct answer is D. All of the above answers are ways a good trip counter can be incremented on Chrysler OBD II vehicles. We've covered a lot of information about OBD II operation. Now let's apply that information to actual vehicle conditions so you'll be more familiar with OBD II when you're working on vehicles at the dealership. We'll take a look at 2 different examples of vehicles failing OBD II monitors, and then show how OBD II records a good trip after the necessary repairs are made. We'll be using the DRB3 scan tool to watch the OBD II system at work. I'm sure you're familiar with the DRB3, but if you need a refresher course, refer to the May 1995 MasterTech that covered recent changes to the DRB3, or take a training course on OBD II or the DRB3. In our first example, this Stratus fails the O2 sensor monitor. To gain an understanding of how the mill comes on, we need to watch what happens during OBD II operation. In order to see the O2 sensor monitor running, we hooked up the DRB3 and took the car for a ride. As we told you before, a monitor's enabling conditions must be met before a monitor will run. The enabling conditions can be seen on the DRB3 by pressing Help or F1 under OBD II Monitors. Here we can see that the O2 sensor monitor is running. As we said earlier, the O2 sensor monitor checks the output voltage and switch rates of the O2 sensor. And now we can see that the vehicle failed the monitor. When we checked on the DTC, we had a maturing code in the PCM's memory. That's what is known as a one-trip failure of a two-trip fault. As you know, the vehicle has to fail the monitor on the next trip to turn on the mill. Once again, the O2 sensor monitor ran after its enabling conditions were met. And as a result, the vehicle failed the monitor for the second time in a row. Here we see the task manager requesting the mill be turned on, and the mill does indeed come on. And the check of the Read DTC screen shows the DTC stored in memory. Now you've seen what actually happens when a vehicle fails an OBD II monitor. At this point, a diagnosis and repair would be made using the Diagnostic Procedures Manual and the DRB3 scan tool. Let's assume that the repair was made. Remember, you should not erase faults until after a good trip has been completed. So then we needed to verify the problem was gone by driving the vehicle again. Remember, in order to record a good trip, the O2 sensor monitor has to rerun and pass. The enabling conditions were met, and the O2 sensor monitor ran again. The mill was still on at this time. The vehicle passes the O2 sensor monitor, and we have just had our first good trip. We needed 2 more good trips to turn off the mill. The O2 sensor monitor ran again, and the vehicle passed the O2 sensor monitor for the second time. A check of the global good trip counter showed the counter had recorded 2 good trips. That means we needed 1 more to turn off the mill. The O2 sensor monitor now ran for the 3rd time in 3 successive trips. After the monitor passed for the 3rd time, the global good trip counter showed 3 good trips. The task manager is requesting the mill be turned off, but the mill won't turn off until the next vehicle startup. When the vehicle was restarted, the mill was turned off. That's how OBD II turns the mill on and off for once per trip monitors. However, in order for the DTC to be erased from the PCM's memory, the vehicle would have to go through 40 warm-up cycles without a fault. Later on in the program, we'll tell you about the data that is stored along with the DTC when a fault is set, called freeze frame data. But now, let's look at another example of OBD II monitors at work. Let's go through an example of OBD II operation for continuous monitors. We're going to use this new minivan to show you the catalyst damage misfire monitor. You may recall that the catalyst damage misfire monitor flashes the mill when it detects a misfire in more than 15% of cylinder firings during any 200 revolution cycle. We won't see any maturing codes because the catalyst damage misfire monitor is a 1-trip fault, and the mill will be flashing after the fault has been set. We drove the vehicle and recorded the monitor at work on the DRB3. Pressing the Help button under OBD II Monitors showed the misfire monitor's enabling conditions. And after those conditions were met, the misfire monitor became active, looking for engine misfire. When the vehicle failed the catalyst damage misfire monitor, the mill immediately began flashing, and the DTC, the freeze frame data, and the similar conditions window were all stored. With a flashing mill, the driver should immediately ease off the accelerator. Once the vehicle is out of the operating conditions that produced the 15% misfire, the mill stops flashing but will remain on. Once the vehicle has a DTC recorded, you can use the DRB3 to read the code and begin your diagnosis. It's important that you don't erase the code from the PCM's memory at this point. Again, refer to the Diagnostic Procedures Manual for specific information. After diagnosing and repairing the minivan, we went out on the road and got the vehicle into the misfire similar conditions window. Here's a look at the task manager showing the mill light on, and the mill on the instrument panel is on. Before the mill could go off, the misfire monitor had to run and pass 3 separate times while the vehicle was in the misfire similar conditions window. With the vehicle in the similar conditions window that was recorded when the monitor first detected engine misfire, the misfire monitor ran. The misfire good trip counter records a good trip when it sees 1,000 engine revolutions with no misfire. When the misfire good trip counter recorded 3 good trips, the mill was extinguished on the next key cycle. The DTC will be cleared after the successful completion of 40 warm-up cycles. So now you've seen firsthand how OBD II operates. You'll need this information as more and more OBD II vehicles come into the dealership for service. In our next segment, we'll talk about how OBD II will affect you as a service technician. As technicians, you know that part of your job is keeping up with the many changes to Chrysler vehicles as they come about. And as you've seen so far, OBD II has brought with it plenty of change. But these changes actually benefit service techs for the most part by providing added diagnostic ability. The change most obvious to technicians pertains to how faults are set. Prior to 1994, all faults were one-trip faults. If the PCM detected a problem, the mill would come on right away. But as you've seen, OBD II monitors are two-trip faults, except for the catalyst damage misfire monitor. OBD II passenger cars and the new minivan have one-trip faults for comprehensive components. These are engine, transmission, and transaxle inputs and outputs. Jeep and truck comprehensive components can be two-trip faults. Another change is that with OBD II, many more faults turn on the mill. Before OBD II, there were 5 to 10 faults that would turn on the mill. On OBD II vehicles, there are approximately 50 faults that turn the mill on, plus one that will flash it. In addition to OBD II's system-wide responsibility, one reason for this increase in mill-related codes is that the PCM must monitor system and some component deterioration, as well as its function, and it can detect, for example, a sluggish O2 sensor. Just as OBD II caused changes in turning on the mill, it also changed the way the mill is turned off. With Chrysler OBD and OBD I, the mill was turned off at the next vehicle startup if no fault was present, except for 1987.5, 2.5, and 3-liter S-MEC minivans. But as you've already seen, the mill must stay on for at least 3 good trips on OBD II vehicles. The many changes brought on by OBD II also changed Chrysler's diagnostic philosophy. Before OBD II, it was a standard practice to erase fault codes before a repair was made. Now, however, you should not clear fault codes from the PCM's memory until after the vehicle has run and passed the monitor that set the fault, or the monitor is required to increment the global good trip counter. OBD II has also meant an increased responsibility for accurate diagnosis. Improper diagnosis and parts replacement may lead to a parts recall on all vehicles that use common parts. Ironically, all these changes actually brought help for technicians in the form of increased diagnostic capability. The PCM does its share of diagnosing problems on OBD II vehicles. For one thing, as mentioned earlier, it not only monitors more items, but it monitors items for deterioration. It is also able to indirectly monitor mechanical operation through its electronics, an example of an electronic module monitoring mechanical hardware. The changes that OBD II brought also necessitate enhanced DRB3 software to aid technicians in analyzing OBD II vehicle data. Chrysler has industry-leading scan tool diagnostics that provide a lot of support to technicians. In our next segment, we'll tell you more about OBD II data and the DRB3. But first, try answering another review question. Fault codes should not be cleared from the PCM's memory until what takes place? A, the vehicle stores a different maturing code. B, the vehicle reruns and passes the monitor that set the fault. Or C, a repair is made on the vehicle. The correct answer is B. You should not clear fault codes from the PCM's memory until after the vehicle has run and passed the monitor that set the fault. You might think that OBD II is going to make your job of diagnosing and fixing vehicles harder. But the OBD II requirements keep the technician in mind with what is called freeze frame data. OBD II freeze frame data provides service technicians with vehicle operating conditions at the time the malfunction was recorded. This freeze frame data is captured by a portion of the PCM's memory that acts as a small onboard data recorder. It's part of the CARB OBD II requirements that certain operating conditions must be recorded along with the DTC when a fault is set. Freeze frame data can be read with the DRB3, giving you critical fault-related engine data to help find the problem. When freeze frame data is recorded, it's also assigned a priority or a kind of ranking of the severity of the failure. Priority 0 is non-emission related, so no data is stored. Priority 1 is a one-trip failure of a two-trip fault that is not fuel system or misfire related. Freeze frame data that has a priority of 2 pertains to a one-trip failure of a two-trip fault that is fuel system or misfire related. Priority 3 freeze frame data is recorded when there is a two-trip failure or a matured fault that is not related to fuel system or misfire. And finally, Priority 4 is assigned to data that is recorded when there is a matured fuel system or misfire fault. The relationship between freeze frame priorities is pretty straightforward. Priority 1 and 2 are unmatured two-trip faults. Priority 1 would mature to Priority 3 since they are both non-fuel system or non-misfire related. Likewise, a Priority 2 fault would mature to Priority 4 since they both pertain to fuel system or misfire. Fuel system and misfire related freeze frame data will overwrite other data of lower priority because these continuous monitors detect conditions that greatly affect drivability and emissions. Be sure to erase the freeze frame data after the monitor that set the fault runs and the vehicle passes. This will free up freeze frame memory to record new data. The data that is captured in the freeze frame includes the fuel system status in open or closed loop, the calculated load percentage, engine coolant temperature in degrees Fahrenheit, the short and long-term fuel trim percentages, absolute map vacuum in inches of vacuum, engine RPM, the vehicle speed in miles per hour, the DTC that caused the freeze frame, shown in hex, and the freeze frame priority from 0 to 4. So you can see there is plenty of data to help you diagnose drivability problems on an OBD II vehicle. You might be wondering, how is the freeze frame data erased from the PCM's memory? Well, that depends upon its priority. Priority 1 and 2 freeze frame data will be erased along with the maturing code if the vehicle passes the monitor that originally set the fault. All freeze frame data can be erased with the DRB3, but be sure to erase it after the vehicle has passed the monitor that set the fault. Disconnecting the PCM will erase all DTCs, freeze frame data, good trip and warm-up counters, similar conditions data, and the readiness indicator. Earlier in the program, you heard the term similar conditions window. CARB defines the similar conditions window as vehicle operation within plus or minus 375 RPM and plus or minus 10% of map vacuum for values that were stored when the vehicle originally failed either the fuel system or misfire continuous monitor. CARB requires that the vehicle be in the similar conditions window before the mill can be turned off for fuel system or misfire faults. And before the freeze frame data can be erased, the vehicle has to pass the monitor in the similar conditions window that caused the freeze frame data to be recorded. However, the one-trip freeze frame data can be erased if the vehicle has 80 global good trips outside of the similar conditions window. You can think of the similar conditions window as a replacement for the global good trip counter for fuel system and misfire faults. For vehicles with the FCC and SBEC 3 controllers, the similar conditions window is recorded when the first occurrence of misfire is detected. There is quite a lot to know about OBD II operation. If you would like more detailed information, you should look into the Chrysler Technical Training Course on Onboard Diagnostics 2, number 083-0516. We hope this program on OBD II highlights has been helpful. That's all for this month, but we'll see you next month on Master Tech.
News.